use transformations. And I'll get back in where we should be. Guys, I have a function I brought in, looks like this. Y is equal to log base 3 and it looks like this. Okay. I like to sketch. Guys, by the way, have we looked at the parent graph or a log? Have we seen a parent graph or a log? Did I do an exponential? Did I graph one day? Did I do 2 raised to the x, I think it was, and I did a table? We graphed an exponential. Okay, so on the side here, it says log base 3. Let's just quickly remind you what a log graph looks like. Just basic graph. And then we'll see what this might do to it. Some of my students may know. If so, please tell me. Suppose I want a parent graph to be associated with a basic log. What on earth does a log function look like graphed? I know what a quadratic looks like, it's a parabola. I know what a linear looks like, it's a straight line. What is a log function look like? Anyone have an idea? Not a parabola. I'm going to ask you this though, to lead into it. Did we, remind me now, I think we did one day, you may have forgotten. Did we have a graph that looks something like this? Let's place it right here. 1. Did we have a graph that looks something like this? Somewhere in your notes. And had a y-intercept at 1. And I think I may have labeled that. Does anyone remember how I labeled that back then? What were we discussing to get a graph that looks like that? Please remind me. Oh my goodness. That's an exciting class before the break. Come on now. What was that represent? Where did that graph come from? I think I did through a table. Y is equal to, what was it? I think it's 2 raised to the x. So let's call it in general here, y is equal to a raised to the x. For the purposes of what I'm going to do here. At this point, a raised to the x. And then I think this will bring back memories. There was a graph that looks something like this. There's an x-intercept at 1, and it looked like this. And I think I graphed that with the table the other day. Does anyone recall what its name was? The red one. What was that graphing? What does that represent? It's not a quadratic, it's not linear. What was that representing? Anyone?
That's just a y.
Well, I'm looking for a word here. What does that red graph represent? In fact, I heard one student in class when I did this, I recall, he was telling me, Professor, these two are inverses of one another. Because the reflecting line was y is equal to x. And one graph is a reflection of the other across that line. Who recalls what on earth was I discussing for the ray? Go for it.
Was it log 2x?
Yes, log base 2x. It's a log graph. So the exponential looks like this. The log looks like the red one. Right like this, guys. This represents y is equal to, let's say, log base a x. Yes or no? Will we accept that? Is that what it looks like? Now, when I graph this one, you think of the parent graph, we'll do this parent graph here, and then we got maybe have to do some things to it. What do you think, guys? Can we do do that. By the way, will you accept that as my parent graph? The reference for a log graph? It'll be an exponential 2 raised to the x. And then a student told me, Professor, you were talking about a log base 2 of x. Is that true? And we have the two graphs and there are inverses of one another. Now, someone remind me as I close this down, in terms of transformations, does anyone have an idea? Because I do see that subtract 2 on the end means a vertical shift down 2. So I need a parent graph, I'm going to start doing these transformations on that parent graph. I definitely know there's going to be a vertical shift down 2. Does anyone recall anything else from transformations that we've done so far that might tell you more to be done? Phil?
Reflect over the y-axis
Why?
because it's negative x.
Okay, you're saying first, Professor, the x should come first. We saw other functions that we had to do this. Rearrange it, and then before I get that reflection, I should actually factor out that negative and make the inside part, guys, look like, let me step back and look at it. Does it look like that? So is this, with the negative stuck out front, equivalent to black? It's really different. Are they equivalent? Now, Philip says if they are, Professor, I remember back when we graphed some other functions, that if there was a negative sign inside here, which there is now, there was a reflection through the y-axis going on. If the negative sign were way out here in front, there's a reflection through what? The x-axis. Have we done those transformations before? Same transformations. So I got a reflection through the y-axis. This tells me there's a horizontal shift 9 to the right and a vertical shift down 2. I'm going to do all that where? On this parent. This is my parent graph. So I got to start out with it. Guys, let's get this done and we'll jump back into that handout. Okay, let's put the parent graph on first, as we usually do. And I think the classes tell me, yes, Professor, I'll accept that red graph as a basic parent graph for a log. X-intercept at 1. Looks something like this. Guys, we label this as I move along. Log base 3, let's call it. That's my parent. Now we want to go from left to right. This tells me, Philip, remind the class, what does this mean to do with that graph?
Reflect across the
Reflect across the y-axis. Okay, so let's go reflection across the y-axis. And by the way, guys, if I reflect across the y-axis, I'm on top of the board, so watch. In blue, I'll put it in blue. This point now is here. It was there, now it's reflected across the y-axis. What might the graph look like? Please, I'm going to just do it before I mark. Does it look something like this? If it's reflected across the y-axis. Here, yes, I'm going to put it down here like this. More like this, and see if you guys agree. Does it look something like that? The red one reflected across the y-axis. Labeled as, at this point, since I've done it, y is equal to, what was this, log base 3. All I've done is this. I just pay attention to the negative sign. Is that true? Now, let's go further. Philip, I'm coming back to you. Give me some good input here. Tell the class what the x subtract 9 tells me now to do with that blue graph.
move it to the right 9.
Move it 9. Now here's the problem. We'll move it 9. Definitely on the blue, this negative 1's going to land at 8 if I move it over 9. Let me try to put this in green. Say 8 right there. So that's negative 1, horizontally shifted 9 to the right. Here's the issue. What else is being shifted 9 to the right? Besides that negative 1 that's on that blue graph. Yeah, there's an asymptote here. In fact, a vertical asymptote. See this right here? Is that an asymptote? The y-axis? So is that y-axis also being shifted over 9? So is it now over here see it? Is it now here? My asymptote, y-axis has been shifted over 9. My point over here on the other side, negative 1's been shifted over. And my graph should resemble the blue graph, you do it in green. So I say, Professor, looks, at this point, it looks something like this. Would you guys agree? I'll draw the scale. That green now represents at this point y is equal to log base 3 negative x subtract 9. Close that up. That's what the green represents. Now, am I finished with the transformations? I have one more transformation, and then I'll have the final graph. What's my last transformation asked me to do? Take that green graph and do what to it? Vertically shift it down 2. That's no problem. I can shift this down 2, of course. Easily done here on the green graph. What do you think I'll be asking, though, on that final graph, besides just shifting down, to get a good graph? That I usually ask on the others that we did in class. Go for it.
The y-intercept?
The x and y-intercept. So I'd like to find the x and y-intercept on my final graph, and I'll plot those, and we'll get it. So on the final graph, and I'll do the final graph, I've got blue, red, all this business going on. I guess I'm stuck with maybe a black here. Okay, let's try and find the x-intercept. Guys, watch carefully. Set y equals 0, of course, in my function. Log base 3. If you want to leave it in the original raw form, go for it. That's what you must solve to find the x-intercepts. I would suggest you move that 2 over first in an attempt to do this. Now, can someone in this clever class tell me, and you gotta be clever, what would you suggest at this point to go further in an attempt to get x? You gotta solve for x, the x-intercepts. Someone in this clever class tell me what would be nice to do with x.
Minus 2.
What was that?
It's minus 2. And it's gonna be just.
Oh, it's minus 2 here.
Yeah.
Here I go again now. Now tell me, is that true? Now tell me what that means. That means 3 raised to what? Second is equal to what? 9 minus x. That's the definition of a log. I started out with in class today. I love that. If you know the definition, the word log's gone now. You changed it to an exponential by definition. So the word log is out. I've got a nice equation here that's 9. Well, 9 subtract x. Are you kidding? If I solve for x, please tell me, guys, what is it, 0? So I've got 0, 0 as an x-intercept. Now, this one's not too exciting. If I've got 0, 0 for an x-intercept, does that imply also if we go ahead and find the y-intercept, I'm going to get 0, 0 again? I have to. I've got to get it. Let's make sure, though. Find the y-intercept, make sure we're working with the right function here. Y is equal to log base 3, and inside there would be 9 subtract 0, subtract 2. If I go back to here, and replace x by 0. Guys, this much right here merely says, and you can see it, it's log base 3 of merely what, 9? Subtract 2. What's the log of 9 base 3? If I meet you in the hallway, you don't have that answer. You know what I'm starting asking you when I see you in the hallway? I'll tell you a little short story about what a couple of students did. One time I tried to ask them a question. What's the log of 9 base 3? Shame on you. What's at least this? Shame on you. What is it?
2.
It's 2. Then subtract 2, yeah, there's that 0 that we thought would show up, and it did show up. Then the log of 9 base 3, 2. Yeah. Now I know the y-intercept is 0, 0, which I think I've already plotted. I think I did. No, I haven't started to plot yet. So guys, the x and y-intercept, not too exciting. It's there. Is that true? X and y-intercept. y-intercept both 0, 0, I think. Now where's my graph? Am I finished? I found the x and y-intercepts. I thought that would help me out, but in this particular case here, it's not exciting, 0, 0. If we did the math correctly, and the graph should resemble the green. I think the green was the last I did. Is that true? Now, should that be over here now? Doing something like this? Passing through 0, 0 or not? For the final graph. And by the way, would that take care of this being shifted down 2? With this point right here being shifted down 2, would this pick it up as I did it? Do something like this, guys. Can I say in black here, does the final graph look something like that? I'll extend it. The green graph, black graph is the black graph representative of the final graph. And I would say, well, if Professor, we want to do it more precisely, I know when you shift down 2, this point right here would be shifted what, down 2? So should my graph actually pick it up? So could I now revise it and make it still look the same, but just revise it and pick up and make it a little bit more detailed? So guys, tell me, down 2, I'm going to do it right now. First, does anyone accept that out 8 down 2 might fall on this graph with that vertical shift down 2? And we said it's also supposed to go through 0, 0. Is that true? Now, I'm not drawing the scale. That's what's throwing me off here. Move this down just a little bit here. Is it possible to now have that come up like that? And let that be the final graph? Something close to that asymptote. Pick that up, come on up, go through 0, 0 as we thought it should. Could I say now maybe that looks better? For a final graph? Yes or no? Jeez. Now, Joseph, if that graph is correct, and notice that asymptote over there, the graph does not touch it. Please tell the class, Joseph, based on my final graph, the black graph, what would you say the domain of this function should be? Up to 9, not including 9. Is that true? Now suppose the graph had not been given to you. I didn't graph this for you. And I had asked you, without seeing all this, I didn't do this, I merely said, quickly just look at the original function, no graph. Now tell me its domain, based on what we've done in class, what's the domain on the original function? How does one find it? And we just had that on the handout. This part inside here must be what? By restriction. Greater than 0. We did a few of those domains earlier. Is that true? If I go ahead and solve this, do a reverse, I'm saying the domain is x is less than 9. Joseph gave me this based on the graph. Are they the same? Are we saying the same thing?
Yeah.
And they have to be the same. So I can pick up the domain on the original function and then graph it and pick up the domain based on the graph, and they had better agree. Same domain on that. Range, Joseph, we're going to come back to you. How about the up and down of that black graph? Thank you. And of course, my x and y intercepts were so boring here, 0, 0. Jeez. Make sense, guys? So I had to do that before I move on with that handout there. And I think that's all I would need to do. Oh, hang on. Can someone tell me, based on the black graph, see if it'll work, where am I guaranteed, hang on, that this will be true? Place it on the side here. Based on the graph, when, what, where, when will that happen? When is that true? And look at the graph. Staring at you. Trying to tell you. Yes? Okay, real loud. Okay, less than zero for a graph tells you look where? Below. So I like to know where is that black graph, if it's drawn correctly, when is it below the x-axis? And it looks like it's below the x-axis, guys. Here goes, and see if you agree, isn't here. So I would think, based on that, an answer would be, what's the answer? Looks like 0 through what? Not infinity, 0 up to what? 9. And it looks like in interval notation, so you guys will agree, should it be written like that? Is that true? Okay, hang on just 1 second, 1 second, let me check here. Oh boy, I get carried away with this before I get back to the end now. Let me try something real quick that might be doable for us. Let me find something in this interval, just at random. Something between 0 and 9. I'm gonna go back and replace x by it and do my calculation, and the answer had better be negative, which is less than 0, if this graph is correct. Let me find something that might be nice. Or maybe some of my students can help. Between 0 and 9, guys. Well, if I try 1, I don't know how exciting that is. 1's in here, so 1, replace x by 1, that's what, 8? There's no nice log 8 base 3, is there? Trying to find something doable. Anyone see one that might be doable? I've tried 1, 2, I get 7. A 6, if I put a 6 there, here we go. 9 subtract 6 would be what, 3? Right. Log of 3, base 3. What is log 3, and we get a 3, well, the student gave me a 6, 9 subtract 6. What's the log of 3, base 3? 1. And what's 1 subtract 2? Minus, negative. And there's other numbers which should also work based on that graph. Making sense? Now, how to do that? Let me step to the side. This one was not that exciting because of that. I like it when the x and y intercepts different. Yeah. Okay, part 2, arena. Let's try to get this out of the way. Let me check and see if I have it right here to maybe get out of the way here. What's the next part there, arena? Coming up, what's coming up next?
Solve.
I want to solve. Is it on the 4.6, is it?
4.5.
4.5, hang on now. And it says, solve. Okay, guys, we'll solve a couple of these. Now, see, the next part coming up is what? Change of base. I may hang on to that for later. Okay, solve. This is where I'm going to stop and go into the trigger shortly. Tell me the first equation they're asking me to solve.
Log base 2.
Log base 2.
Base 2. 3x plus 4
3x plus 4.
equals 5.
Oh, my goodness. We're going to make sure I have come down correctly. That? It's a breeze. If you know the definition of a log that we started out with in class at the beginning. Anyone quickly get rid of that word log and tell me what it means? Get rid of the word. What does it mean? It means 2 raised to what? 5th is equal to this. Done. Word log's gone. I guess by definition means that. If I should finish that up, I think that's even better here. This is 32 equals 3x plus 4. Now watch me mess up on the math here. 28 equals 3x. It looks like x is going to be equal to 28 over 3. Check my math here. And we're done. That first one is finished. Karina, tell me, was there another one there?
Log base 7.
Base, how much?
7.
7? Okay.
X squared plus 4
X squared plus 4
equals 2.
equals 2?
Yeah.
Looks like that. Oh my goodness. And when we solve for x, can I do it? Yeah, tell me what it means. What's this particular one mean? Means 7 squared is equal to x squared plus 4, and the word log's gone. I see right quick, what's that, 49 subtract 4, 45 equals x squared, yes or no? I think it is. And then do a square root, looks like plus minus at this point. Square root 45 is not perfect. Does anyone know what square root 45 looks like simplified? 3 radical 5. Now please tell me, can I accept both? Do I take 3 radical 5 back to the original, or negative 3 radical 5 back to the original and do what I gotta do? Will they work? Yes, because it's being what, squared? Turned into a nice positive, beautiful. Was there another one? Oh. Okay, hang on. What, is the next one coming up the last one? Is the last one on that handout? What was that next one? Whoa, whoa, whoa. Oh, it's e raised to a power. E raised to what?
2x plus 5
Okay.
equals
8,
8. 8.
like that? And we should solve for x. There's no log in this one. Any ideas? Like I said, I've been bragging on you guys. Stuff it. Say it again. You got to rewrite it. Since there's no log there, can you rewrite it and put a log in? That may help. So e raised to the 2x plus 5 is equal to 8. Joseph, tell the class what that looks like rewritten with a log. And by the way, that base e tells us it's a natural log. It's an ln. Tell me what it looks like. Now, hang on. Mark what to go out me. 8 equals 2x plus 5. He's exactly right. Those two statements are saying the same thing. Now you can solve it for x. Guys, you want maybe a strange answer, move that 5 over, put it up front, and have this, and then divide by 2. Now, I know it looks a little strange here, 2's cancel of course, but that is x. Guys, looks like it's negative 5 plus ln of 8 divided by 2. Would you guys agree? Is that x? You're finished. Who would think it would be that easy if you just took the time and rewrote it in log form? And there it is, the answer. Now, I'm about to finish this up. I'm going to start trivia shortly. Let's give you a little introduction to chapter 5. All right. Arena, how about the handout? Flip that over. Whew. Boy, am I ready for something here? The one I passed out today, was there a series of equations to solve? Where I am. Yeah. Was there at the top there quite a few equations to solve? Yes or no? No, maybe not. Let's see. The one I gave you guys today. And this is the one I gave you today. Oh, I see what it is. I see what it is. Guys, jump down to the very last problem down there. And we're closing this down. And moving to the little tree here. Okay. Rena, I saw what the problem looks like. Now, I want you to work out the last one. I think it says show something. Now read that to me. Base A?
Yeah.
Okay.
Square root x plus square root x minus 1.
Okay. Hang on now. That's in parentheses, I think.
Plus log root base A.
Okay.
Parentheses square root x minus square root x minus 1.
to 0. Now, the reason I brought this in to close that down, I usually give one like this for an extra credit. See how many students are going to follow me and see if they make some sense of this. Anyone tell me, to close this down, what would you do here to show that this right here, all this left-hand side is merely that you have to verify it? You want to have an idea?
It's a product.
Hang on just a second. Yes?
Would you use like a reverse of the product?
Okay, beautiful, here we go,
It
here we
says
go.
plus, you multiply.
Here we go, beautiful. If I'm adding logs, and I am adding logs, students tell me, Professor, why not use the product property? In other words, backwards. It's already been expanded out for me. So backwards, I think, I don't want to take any of the credit here, but tell us more about what you think. Tell me more. What should I write? You're exactly right, though. Go ahead.
Log A is the base, and then square root of x plus square root of x minus one.
This is beautiful. Tell me more.
And yeah, in parentheses times square root of x minus square root of x. Is it minus one?
It is.
Equals 0.
Now you want to show that. Thank you. Exactly. I'm using product property. Just put it backwards though. Now what I'm going to do is, now write this as log base A. Now, can someone, and I'll remind my class of this, if you should multiply that out that was given to me. This to me looks like an A plus B type times an A subtract B if you want to do it quickly and find the product. And I know A plus B times A minus B, you know that also, is A squared subtract B squared. Is that true? Where A is square root X. So that's square root X squared. Subtract. B is square root X minus 1 squared. Guys, do we agree? Is that what it looks like if I use A minus B times A plus B? Or you guys can just fully expand it out. Going further, this now looks like this. Log base A. Inside there, of course, if I square the square root X, I get X. If I square that next square root, I get this. Okay, let's see now. X's are canceled inside there. And in fact, watching my signs here, yeah, the X's canceled. I think I'm left with, as I heard, merely a 1 inside. Am I? So here's X, subtract X, this turns into a plus 1, X is canceled. Now, please tell me, why can I justify, Professor, you're finished? You've already verified it is 0. Go for it. A raised to the 0 is equal to 1. That's what this says now at this point. The log of 1 base A is 0. And we showed it. That's what we have to do, show it. We showed it. With some help. Nice. Okay, guys. Now, I'll probably clean up a little bit more tomorrow on logs in this chapter 4. But basically, chapter 4 is finished. Woo! As an instructor, I'm glad. Because it was heavy. As a student, I'm sure I'd be very appreciative of it now being at least done. It's a heavy chapter. Now, before I jump into it, in chapter 5, I don't think I shared this little story with you. I like to, when I see you outside, and sometimes I'll see my students out shopping, sometimes I'll see them out shopping, wherever, I'll see on campus, wherever. And if I see you and you see me, I'm going to ask you a math question. So I may come up to Philip and say, Philip said, oh, Professor Anthony, how are you doing today? Philip, what's the log of 27 base 3? Oh, I expect that, Professor. I'd like to say good morning or good afternoon, have a good day, now to move on. No one has any question for you. Joseph, when I see you? PK, when I see you, you know me by now. I have a question for you. So, I can tell the class, I have a question for you. So, two guys in the parking garage, when I was parking, they saw me. They were sort of on one level, I was down here on the other level, but they saw me. Professor Ramsey, Professor Ramsey. I looked, oh, come here. They knew I was asking a question. They just shouted out, have a good day. They disappeared. They disappeared, they were out. You guys, if you see me out, get ready. I'm gonna have a math question for you. I'll say hello to you and have a good day. Math question for you. Now, chapter 5 is coming up. This is a chapter I've been waiting for. I've been waiting for it. Now guys, I'm gonna give you a short introduction, and it's gonna really take off tomorrow. And I'll tell you more about this quiz coming up tomorrow. By the way, I expect that 11:30, I'm here at 11:30 tomorrow, yes. I'm expecting that room to be packed. Packed. To get ready for this quiz. And Friday, probably some maybe out in the hallway waiting at 11:30 to get ready for the exam. Okay, here we go. Let's leave logs, let's leave exponentials, let's focus on a different topic altogether. I think it's going to be much easier for us to deal with it. I'm so rushed here, let me leave that over there for right now. Now, here we go, this is chapter 5. I brought in something just to introduce this, and I think on those handouts, I've got those handouts probably give you tomorrow. I think, did I actually get a chance to start chapter 5? Does it say 5.1 or 5.2 or nothing on this one? Oh, 5.1? It does say 5.1.
Yeah.
So it's a chance for me to at least get an introduction to this. Now guys, this chapter's gonna take off. And you will find it so much easier. Oh my goodness, Professor, let's not go back to logs and exponentials. I think you see this is gonna be nice. So you part one, guys, here we go. I'll get started here. This is all about this. Angles and their measure. Watch carefully. As soon as I do this, I think, based on previous classes, I think every student in my previous classes somewhere have seen what's coming up in this next chapter. And they like it. No logs to worry about, no exponentials. Now what is it though? It says angles and their measure. If I should do this, at this point, like that, every student probably in class would say, Professor, that's an angle. From what I know what an angle looks like, that's an angle. And then the topic was, the title in your textbook is, not only angles, but also their measure. Now, reflecting back to middle school, probably, the teacher was showing you how to measure the size of an angle. And they passed out an instrument to you, more than likely, and let you use that instrument, and you lined it up correctly, they smiled, you smiled, and you read the instrument, and you said, oh, that angle has a size of something. What was that instrument known as? A protractor. They gave you something known as a protractor, and they showed you how to place it on this, and then you looked at some numbers on that protractor, and everyone smiled, and you said, oh, this has a size of 30. And the units here would be degrees, 30 degrees. So this angle has a measure of 30 degrees. That's its measure. What we want to do here, I'm not passing out protractors. And by the way, just out of curiosity, what was the other instrument that they usually passed out for you to draw circles?
Compass.
A compass. compass. I'm not passing out those instruments here. What do they want us to do? They want us in an upper level class to do this. They want us to capture this angle like this. This may not look exactly right. They want you to capture that angle in a circle. Different way to measure now. We're going to get away from degrees and a protractor. And guys, I'm going to say right now at this point, I'm going to throw in 30 degrees. I mentioned that. That was in middle school, 30 degrees by a protractor. You say, Professor, it says to measure that. How else can I measure it? If I don't say degrees, is there another way to measure it? There is another way to measure it. As I place it on this circle, and by the way, we love in math a particular circle for it to be placed inside. We like a circle known as a unit circle. In other words, its radius is 1, and the length of 1. That's the one we like. Of course, there are bigger circles, smaller circles, but the one we really like to work with is a unit circle, 1 unit of the radius. Guys, what am I asked to do here? We'll change the measure into something that they probably do not do in middle school. I'm going to ask you, could you come up with the length of this arc that's being cut out of that unit circle, whose radius is 1, on that unit circle? And I'll accept that as another way to identify its measure. Here it says real quick here. Okay, now tell the students, oh, how did you arrive at? Now, you quickly gave me a pi of 6. Someone give me something that may have to be done first for those who've never seen this. Now, what on earth is the length of this arc that 30 degrees cuts out, intercepts out on this unit circle? Yes?
Find the circumference of the circle.
Thank you. First, find the circumference of the entire circle. Guys, the standard formula for circumference, the length around the circle, is 2 pi r. Now you understand now why we like r to be 1, a unit circle. If I replace r by 1, I'm looking at a circumference of 2 pi. Now that's the full circle around the length. I don't have the entire length. I just had this little piece of it. So I need to come up with, hopefully, a ratio, a fraction of. What fraction of the entire circle of this 2 pi do I actually have? So step 1 is the circumference. I love that. Okay, can someone give me a ratio that I'll now apply to that 2 pi, the full circle, and get that little piece I want? Joseph. Look at that. I'd like that, something else first. Something else, but this is for the sake of those students who may have never seen this. I've got a 30-degree angle. What's the size in degrees of a full circle? 360. Do we agree with that, guys? So I have 30 degrees, so let's form a ratio. I will compare 30 to 360, which I could reduce down to, I think, 112. There's my ratio. There's my fraction. I compare 30 to 360. And then I'm going to do what Joseph was telling me. I'm going to now take 1/12 of that full circumference, which is now going to give me, if I cancel over here, there's that pi over 6 I heard him tell me, and there's the measure. Now, it's going to take a little while. If I walk up to you and say, I'm thinking of an angle to measure pi over 6, in your mind you're going to think, ooh, Professor, you're thinking about a 30-degree angle. And I am. Except now its measure is in radians. They call this radian measure, not degrees. These are radians. And when I use that word radian, I think about radius. 5 or 6 radians. Now, let's try a few more here. My time here, we're out of time here. If I should go up to now, let's say here, do it roughly here, guys, and show that maybe now I want to consider maybe a right angle. Looks like this. And I should go ahead and label a few things here in addition to this. Guys, the side here is called the initial side along the x-axis. And this side here is called the terminal side of the angle. In case you see that vocabulary. So I've got an initial side, terminal side, and this time I'm looking at the initial to be here and the terminal to be here. I'm looking at a right angle. So I'd like to, with your help, bear with me, lock it up like this. I'd like to convert 90 degrees right angle into this new measure, radian measure. We've already discovered that the circumference is 2 pi. Now, what ratio do you think I need here to show that for 90, Professor, you will cut out,
1/4.
thank you, you will cut out this much. From here to here. 90 degrees will sweep out that much of the circumference of that circle, which I think is what, 1/4? I'm going to do 1/4 of 2 pi. 1/4 of, here we go, 2 pi. And guys, cancel a little bit here, 2 and 4. We get pi over 2. And this is the measure, pi over 2 radians. So now we're going to think of 90 degrees in this new measure as being pi over 2 radians. Now I can do this all day. You snake the angle for me, I can come up with a ratio of 2 pi, like I've been doing here. I did 1/4, I did 1/12 over there, and just rename the measure. That's what's going on here. Now for me to close down here shortly though, it's a little tedious to do this for every angle. I may say now convert 75 degrees. Let's try 75 degrees. I'm gonna give you a shortcut here. Let's try 75 degrees. By the way, I did 30, I did 90. Guys, 75 is in there. I'd like to convert 75, based on what we're doing here today, into, let's put down 75 degrees into this new measure, radian measure.
45 plus 30.
Okay, and now let's get that ratio first. How would I find that ratio if I'm doing 75 degrees? I'm comparing that to what? 360? Can I compare that to 360 or not? Okay, so 75 compared to 360 for the full circle. And guys, what on earth is that? Help me out. Is that one? Whoa, no, it's not. What is it? Help me out. Will that work out nicely for me or not? I've got 75 there. I thought it would be a nice number to work with, maybe not. Can I reduce it down?
We can make 75 as 30 plus 45.
Do it again.
We can make 75 as 30 plus 45.
Oh, I could. You're talking about something else from later on, 30 plus 45 to 75 and get something else. But I'm just talking about this fraction. Help me reduce this fraction down. So 75 over 360 reduced down. I thought we would reduce down nicely. But would that fraction reduce down at all for me?
Both divisible by 5.
Okay, thank you. I was looking at 5 myself. Is this what, 15?
Yeah.
And this is what, 72, I guess? Now, will that 15 over 72 go down again? Make it reduce again or not? By 3?
Yes.
I heard 5 here, maybe by 3. And then what, 24, I guess? I did it quickly. Is it? That's a strange fraction. I don't think the 5 over 24 will go down any further. So based on what we've been doing here, 75 degrees is 5/24 of the full circle, which is for circumference is 2 pi. And then to clean this up, you can cancel here, which would help. Guys, looks like I'm gonna end up with 5 pi over 12, and this is radians, not degrees, to work with. Now, who on earth, I wouldn't, until I hesitated and thought about it, who on earth would think if someone mentioned, I'm thinking of an angle of measure 5 pi over 12. Oh, you are? Yeah, I'm thinking about that angle. Who would think you're thinking about a 75 degree angle? Unless you sit there for a while and say, oh, it's not giving it to me in radians, I'd have to convert it to degrees. That's what this is all about. Guys, we're ready to close down here. Here's the shortcut to do it. If the angle is given in degrees, and they love in math to represent the angle from the Greek alphabet, letters from the Greek alphabet, they love this letter from the Greek alphabet, theta. And they'll be using more from the Greek alphabet to represent angles later on. But theta, they love theta. If theta is in degrees, put the degree mark, and you want to quickly, not go through all this business, and even though this is the meaning, and you want to convert it real quickly into radians, just multiply that number, degrees, by this constant. And that will quickly change this into, let's put it like this, guys, radians. Without you going through all that I went through on the first couple of examples. If it's opposite, angle represented with theta, and it's in radians. Let me use an R for radians. Let's give it to you in radians first. Now you want to go backwards. You want to change it to degrees. You multiply it by a constant of 180 over pi. This will change it into degrees. And they call this conversion factors. Easily done. We're going to try a couple here, then we'll close down here. Let's go back here, guys. We take an angle of size and put it in degrees here. Let's try 135. 135 degrees. Oh, by the way, does anyone remember the special name they gave for an angle like 135 from middle school? They gave particular names to the angles. It was like acute, obtuse, straight, right. Okay, this is an obtuse, but side there. I like to convert it. Okay, so multiply it by, since it's in degrees, right here, get it. Multiply it by that constant, pi over 180. Cleaned it up. And when I say cleaned up, I guess it means to reduce this down if I can. All right, guys, 135 over 180, like a fraction being reduced down. I think at least it goes down by 5, I think. I'm standing here looking at it. I think this might be, help me out, is this 27 or, we'll step back. Is that 27? Is it? I'm doing it by 5 first. And I guess this is what, 36? Yes or no? Now I can reduce down again by maybe 9. This becomes 3, and this becomes 4. Yes or no? Let's reduce the fraction down. Looks like I'm left with 3 pi over 4. And that's how 135 degrees looks now in this new measure called radian measure. Try one more. Now suppose it's given to me in radians to begin with, on the side here. Let's start out with, let me think of a nice one here. Why not? 5 pi over 6. That's in radians now, no degree mark. But you want to go back to degrees for some reason. Here's my factor. Multiply this by 180 over pi. Pi's cancel. This one's a little bit easier. 6 into 180, 30. 5 times 30. There's the angle. 150 degrees. Easy to go from one to the other with those conversion factors. Wow, wow. I see it's almost 3:15. This class ends at what, 4:15? Doesn't it? 4:15? And I'll give you another break and we'll come back to 5:15, right? That's what I like. That's what I love. Everybody should close down though. Now, how many students think they will be with me? Which I think will be very beneficial. If you're with me at 11:30 tomorrow morning for my session over in room 63. How many students think they will be with me? I see some hands going up. Okay. I think it would benefit you in preparation for that quiz. Friday, I'll be here again at 11:30, and that will be a great benefit. two TAs, anything to say?